If I tell you 3 sine x, what is that 3 really kind of going to represent within the picture? The amplitude. You're basically saying, okay, here's my sine function, right? But 3 and negative 3 are going to be my bounds, right? This function always lies between negative 3 and 3, right? So this number in front is always the amplitude. Agree? So if I take this function right here, sine of x over x, and I rewrite that as 1 over x times sine of x, is that the same thing? That's just me like pulling the x to the outside and writing as 1 over x. Then do you see that if I look at that as being like the amplitude, then what I'm doing is I'm trying to draw a sine function. But as I let x get bigger, the amplitude changes. And what is the amplitude headed towards? What is that headed towards as x gets big? 0, right? Fixed over infinity goes to 0. So it's like I'm trying to draw this sine function. But as I go out, the amplitude has to get smaller. Like that, something like that. And so if I'm asking myself where this function is headed, then you would say that it is headed towards, look, it's really weird, this one, because it is going above and below, but it's like as you move out, it's getting funneled into 0. Now, I think I have a better picture of it in my, here it is. So that is actually the graph of sine of x over x. Hey, look at that graph real quick. That's sine of x over x. What's the limit as you approach 0? 1. Right? That's not what we're interested in. We're interested in what's going on as we go out that way, right? So you see, starts out trying to be kind of like a sine function, right? And then as I go out, notice that the amplitude starts to, well, as you can see it here, you see how it kind of like, it's just getting smaller and smaller and smaller? It's headed towards 0. It actually crosses through 0 a few times, many times. But as you move to the right, this window gets smaller and smaller. Does that make sense that the answer would be 0? Now, this is actually a really kind of important function. I was talking to my daughter the other day. Have I told you all about my daughter? She's 9? Okay, well, anyway. I was talking to her. She has like one of these little rubber balls, like almost like a tennis ball, but it's like just rubber. It doesn't have any of the felt or stuff on it. And I showed her like 4 or 5 years ago. I told her that, you know, if you have a ball and you drop it, like if you put a ball up to your forehead and you drop it, like that ball will never come back and hit you in the forehead. Like it's impossible for the ball to bounce higher than the position you dropped it from, right? So sine functions, we like to use them in physics because a lot of things, like if I drop a ball, it's going to bounce, right? So a sine function would kind of model that, except that as you bounce the ball, it's going to be lower and lower each time, right? And eventually you kind of, and then it stops. This function is a better way to model a bouncing ball because it tapers off to nothing, right? If you try and use just a sine function, that's not realistic because the ball doesn't come up to the same height and then go down to this, you know, that's not what happens. So a function like sine of x over x is more useful than the function just sine x. Does that make sense? We call this a dampened oscillator. It's oscillating, but we're dampening it as we go. All right. So we were able to find the answer to that, right? We were able to find the answer to that because we knew that the numerator was bounded over something that was becoming infinite, and therefore the answer was 0. Could we do the same thing with cosine? What would be the limit as x goes to infinity of cosine x over x squared? What's that limit? So the numerator is bounded, yes? Now, what if, just for the sake of confusing you, what if I said plus 2? Is the numerator still bounded? Yeah, it's still bounded because taking the cosine function, adding 2 to it, all that does is moves the graph up or down, but it still has bounds. You don't need to figure out what the bounds are. You just have to convince yourself that it's bounded. So the top is bounded, the bottom is becoming infinite, and therefore the limit would be 0. All right? No work needs to be done. On a test quiz, all you have to write here is that is bounded. Let me know you know what's going on. Bounded over infinity, and that heads to 0, you're done. No work. All right, so I have a summary here of all the different things we've seen. 0 over 0, I'm not going to go through this, but it's basically your little chart there. It's everything that we've done, all the different cases. Any questions?
That's on Canvas?
What is? All these notes are in Canvas, yes. Try this one. You know what, before we do that one, let's do this one. This will help us. I think if we do this one first, we can handle that one a little easier. You'll kind of get where I'm going with this. On this one, James, where's James? James? What form do I have here? When I say form, I mean like 0 over 0, infinity over infinity. Like, what is the form we have? Infinity minus infinity. Everyone agree? Right. We have the form of infinity minus infinity. All right, so you know now, Savannah, I got to get through all these names. I'm kind of just like doing attendance at this point. Savannah? Yes? What do we do when we see that? Some sort of algebra. Good. Okay, so we're just cranking away here. Nas, what sort of algebra do you want me to do here? Just factor it. Okay, so look, no conjugates here, right? There's no roots. Just look, it's a simple GCF, greatest common factor. Pull the x cubed out. And when you pull x cubed out, Juan, what am I left with? Inside that parentheses. 1?
1 minus x.
Yep, okay. Now, Aaron, where's that headed? Infinity. So this is headed to infinity. Let's keep going, Aaron. This is what operation between the x cubed and this parenthesis? What's that operation there? Multiplication. Okay, now what's this headed towards, Aaron? Negative infinity, right? 1 minus a huge number is going to be a negative number. It's going to be huge. So this is headed to negative infinity. Rasul, what do you think happens here? You have a huge positive number times a huge negative number. Do we need algebra? You sure? Think about what this is saying. If let's say I gave you a big positive number, like a billion, right? A billion, whatever. And then I say multiply it times a trillion, but negative. So take a billion and multiply it by a negative trillion, and what's that number going to be? Big and negative, right? So when you have infinity times negative infinity, that's just negative infinity. Does that make sense? Does that make sense to everyone?
Yes.
Okay, so this would be headed towards negative infinity. Do not confuse this. This is not subtraction here, right? This is times a negative. There's a big difference, because if that came out to be infinity minus infinity, we'd be, well, that's the original problem, but that makes sense? All right, so the limit is negative infinity. That's it, we're done. All it required was some factoring, and then we basically took subtraction and made it into multiplication, and then once we had multiplication, we knew what to do. Or we knew what happened. Okay, so back over to this one then. Emily, is Franklin here? Franklin's not here still, okay. Emily, where's Emily? Emily, What do you get here? Can you tell Emily what form I have? Infinity minus infinity. Yeah, we all agree? All right, now I don't think I'm going to call on anyone on this one, but I'll ask for volunteers. Conjugate? Okay, I think you're thinking conjugate because, damn it, the conjugate has worked for us, right? It's our good friend.
It's the roots, right? The roots.
What do you mean the roots? So I'm hearing two things. Conjugate is one thing I'm hearing. The other thing I'm hearing is, can you pull out roots? Is that what I heard? Did I not hear that right? I could pull. Can I pull a root out? Okay. Let me knock these out one at a time. First, let's consider the conjugate. Let's just consider it. I'm going to write it down. You do not write it down. Okay. Let's consider the conjugate. If I multiply that by its conjugate, that's what the conjugate would be, right? And then I have to do it on the bottom also, right? But let's just see what happens here. This and this become x. That's great. And then the middle term should cancel. Now, what about the last terms here? Minus x, what's that? That's really x to the 1/3 times x to the 1/3, isn't it? That's what the cube root means. So when you multiply these, what do you do with the exponents? You add them. So this is really going to be x to the 2/3, right? You add the exponents. 1/3 plus 1/3 is 2/3. So that's what you would get if you multiply these two together. And then that would be on top of the conjugate. We'd have to do the conjugate under here too again. But see, the problem is if I let x go to infinity now, I still get infinity minus infinity on top. So this conjugates have always worked when we had like either two square roots or a square root and like a number, or square root and like x or something. But whenever you have like square roots mixed with cube roots, your conjugate falls apart. All right, so let's go to the other idea. I heard factor out a square root. I heard that also. I like that idea, but I'm just not quite sure how to factor a square root out. So let's try this, see if this helps. Let's just go from radical notation to rational exponents. It's two different notations for the same thing, right? Now I'm going to try and pull something out. Just like over here I pulled x cubed, right? What can we pull out? It's hard to see what to pull out right now. Okay, so who said that? Okay, we do have a common denominator between these two, which would be 6, right? So watch, could I rewrite it like this? Don't ask necessarily why right now, but is this fair? Is this legal? Is that the same thing? Just rewriting 1/3 is, or sorry, 1/2 is 3/6, and 1/3 is 2/6. So now, what do they both have in common? They both have a 6, 1/6, I guess you could say. What I'm trying to get at is this. I'm going to try to pull something out with x, right? X to a power. What power can I pull here? 1/6. I heard 1/6. I heard 1/3. 2/6, which is 1/3, right? I could do 2/6. Now, let me do 2/6 and just see why it works. That's same as 1/3. Why is this good? Well, let's start with the last term. What would I have to have here to get back this? -1, right? Right, -1 there. What would I need here in order to get back this? X to what power? Remember, whatever power here you put, you're going to add this power to it, and at the end you want 3/6, 1/6. So x to the 2/6 times x to the 1/6 is x to the 3/6. And then x to the 2/6 times -1 is x to the 2/6. So if I multiply this through, I'm going to get back this, but this is really this. Right? Now we have turned it into multiplication. This is really limit. X goes to infinity. This is really x to the 1/3. And this is really x to the 1/6 minus 1, like that. This is cube root of x. This is 6th root of x. So what happens now as x goes to infinity? Where is that going? Infinity, right? Because cube root of infinity is still infinity. But then times, and then where's that one headed? Where's all this headed? That's infinity, right? But then take away 1, still infinity. And now you have infinity times infinity, which is way better than infinity minus infinity. Infinity squared, which is infinity. So this becomes infinite. If you let x go to infinity, basically this guy wins. Square root of x gets big too fast. This one doesn't get big fast enough. So this term dominates, becomes way bigger than this one. It becomes a positive number, just gets large. All right. Let me see here. You're going to need to do your homework, right? No, we have not started 1.6. We'll do 1.6 next class. Oh, wait, sorry. No, 1.5. Wait, hold on. I'm lost. You can now try and do all your 1.6 homework. Yes. 1.5, 1.5, we will start next class. Let's pass this around. Sign in, please. Yes. This is that finished up 1.6. Let me make sure I'm finished because I still have 5 minutes. Yeah. So while the sign-in sheet's going around, a little bit about infinity. This whole, I've already said infinity is like an idea, right? In mathematics, there's actually 2 types of infinity. Although I have also heard there's 3, but. So let me give you one example of well, there's 2 types. One of them is called countable, or countably infinite, and the other one is called uncountable. So let's see if this makes any sense to you. Let's imagine that our entire world, our entire universe of numbers are just the numbers between 0 and 1. All right? Just the numbers between 0 and 1. The numbers that are in here are numbers like 1/2, right? 1/2 is in there. The number 1/4 is in here. 1/8 is in here. 1/16 is in there. And I can keep cutting it in half, right? 1/32, 1/64. Do you agree that there are an infinite number of fractions like that in there? Yes? But there's other fractions in here. 3/4 is in here. 7/8 is in here. Right? All these fractions are in here. There's an infinite number of fractions. Can we agree on that? All right. There are those fractions in here just between 0 and 1 fall into the category of being countable, meaning that you can't actually count them all because there's an infinite number, but you could kind of imagine starting at 0 and being able to almost like walk across a pond on lily pads. You could like jump from one fraction to the next and just kind of work your way through, stepping on all the fractions, working your way across. You would never make your way across though, but you could step across the lily pads, all right? That's countable. Another example of countable is just start counting. 1, 2, 3, 4, 5. That's infinite, right? But it's countable. This one is the one that's more interesting, uncountable. So I always am amazed by the reaction of this. Well, not I'm amazed, but it confirms some things I already kind of know. If I go in here right now and I pick a number, right? Just I close my eyes, I reach in there, I grab a number. Is there a fraction that represents that number? I guess what I'm asking you is every number in here a fraction? Yes. every number. So let's take a vote. No matter what point I ever pick, okay, that if I pull it out of there, there is some fraction that I could write for that number. Yes?
Yes.
I heard a lot of yeses. Okay. That's wrong, all right? That's wrong. It turns out that there are other numbers in here that you cannot write as fractions. An example of a number that you can't write as a fraction that you've heard of before is the number pi. The number pi is what we call irrational, meaning that when you write it out, 3.1415, this thing continues. This decimal repeats forever, never stops, and never has a pattern. As opposed to like the number, let's say 1/3. 1/3 is 0.333 forever, right? See, it never stops, but it has a pattern. All the fractions, every fraction out there, every one of them, the decimal either stops or it repeats. The numbers that don't stop and don't repeat are called irrational. And it turns out that they're in here also. The bad news is that you've only heard of a few of them. Like that's one of them. Another one is e. E is another example of an irrational number. Square root of 2 is another example. So square root of 2 is not in here. Root 2 over 2 is though. That's irrational. So it turns out that not only do you have these fractions, but you have all these other numbers in there mixed with the fractions. Fractions are called rational. These are called irrational. It turns out that the irrationals are uncountable, meaning that if I start at 0 and I start trying to walk my way across and I start stepping on the irrational numbers, I can step on one. And then when I go to try and find the next one, I realize that I've missed an infinite number of them. And so I try and get to the next one and I realize I missed an infinite number and there's no like path through. I have a better analogy. I know I've gone over time, but you made me give you a quiz today. So have you ever been out at night and looked in the sky when you're away from the city? Right? Way outside. You got to pretty far outside. What do you see up there at night in the sky? Stars, right? Stars, right? All these stars up there. If you go out and you look at these stars, you can think of the stars as all the fractions, okay? The stars are the fractions. And then the irrational numbers is the black. So you can actually kind of like see the fractions. You can see the stars, but you can't really see an irrational number. It's impossible to like point to it. It's everywhere but nowhere. It's really weird, if that makes sense. I'll talk more about it later. Two types of infinity. What's that?
I said, here's another fun fact about stars, is that starlight